right, now that we know how to take derivatives of multivariable functions, we're going to learn about a couple things we can make using those derivatives. And the first thing we're going to talk about are tangent planes. So I'm sure we all had our fill of planes early on in class, but we're going to learn about a new special kind of plane. So here's like a shape. Let's make it there. There's like a z equal to f of xy. And you should remember that we talked about, there we go. I feel like I'm getting better at these shapes with the little stylus thing. Okay, so we talked about how derivatives tell you rates of change. So you could kind of imagine, our slopey rate of change going down being with respect to x, or our slopey rate of change kind of in the other direction of the surface, kind of being the one with respect to y. And when we combine those two things, we're going to end up with a tangent plane that kind of describes the way that your surface changes with respect to z, or with respect to x and y in a region really close to a point. And just to give you kind of a zoom in of what I'm seeing here, here's like a bendy kind of surface, whatever. And your plane would be something that kind of touches right at a point, and then it lifts off from the surface, and it is straight in comparison to the bendy surface. I don't know if that helped make things any clearer. Just make it kind of curvy surface, flat plane attached to it. So a tangent plane is the 3D equivalent of a tangent line. But since z depends on two variables, it needs a surface that goes in two directions to approximate it. So it's a plane instead of a line. A plane being like a line that stretches on forever in a new direction. And the equation for the tangent plane is going to be oh, this thing is back. I'm so excited about that. The equation at a point x0, y0, z0 of your surface is given by z minus z0 is equal to f sub x, the derivative of f with respect to x, x0, y0, z0. So evaluated at a point times x minus x0 plus f sub y, the derivative with respect to y, again evaluated at x0, y0, z0 times y minus y0, where z is equal to f of xy. And in case it's not given to you, you should know that z0 is just f evaluated at the xy coordinates you care about. And you should know how to take this f sub x, f sub y, now that you know how to take derivatives. And you should sort of be able to tell that this is a plane, because this is going to be a number times x minus x0 and a number times y minus y0, and you've got 1 times z minus z0. That looks just like the equations of planes that we learned about earlier in class. We're going to do an example with a tangent plane real quick, but I just want you to note that tangent planes approximate a surface. So going back to your 1D intuition, when you had a curve and you could find the tangent line, where the tangent line goes kind of tells you where your surface is going to go. You could kind of imagine that, over time it forms this thing that's really close to the surface. So the same way, when you're very close to your starting point on a tangent plane, you're kind of giving a general idea of where the surface should be. This will be next to useless to you for right now, but the same type of reasoning is how a lot of numerical approximation works, like things that actual computers do, and it might show up in future classes for you.